So my question is about this model to map FSC curves. So generally in the published papers, I see the model to map FSC is generally higher value than the map to map FSC. Is there a general reason for that?
So I think one thing to keep in mind is we have to use a different cutoff criteria for judging that FSC, right? Yes. So for a map to map FSC is 0.143, and for a map to model, it's going to be 0.5.
Yeah, I mean, even like some publication have used even like the same 0.143 FSC cutoff, and there is about 0.2 to 0.3 angstrom resolution difference between map to map FSC versus model to map FSC.
Well, I don't think Tom is, I'm not sure if Tom is on, but I think one of the things is that, of course, a model is refined against the map, right? So it's likely to have a better correlation. Oh, Tom is on.
I'm here, but I didn't hear the question.
So yeah, maybe you could restate the question, Christian, just so Tom can hear it.
So I'm comparing the map to map FSC and the model to map FSC. From the published studies I've seen, and even from my own data, that model to map FSC is generally higher than the map to map FSC. Is it supposed to be that way?
They're not directly comparable. Typically, models to map FSC are typically calculated within a map. So that's defining a region. Map FSCs are typically calculated over the entire map. So if you calculate them in exactly the same way with the exact same mass, then they should be exactly the same, yes. But normally they aren't, so you won't normally get the same answer.
All right, thank you.
Yeah, and Alan Roseman actually just said something in the chat here, which are clearly related, is that you know, there's noise in map to map, but in the model to map, the model doesn't have noise.
Can I ask a related question?
Sure.
A follow-up of that. So are there some red flags for the map to model FSC that you must be looking out for? And even the, yeah, let's begin with that. And then I would like to come to the cross correlation values, if there are any.
Well, as far as I know, there's not sort of an accepted, there's no protocol for comparing, for looking for problems in the FSC, but and I'm sure there are others could say more, but you know, I'd be worried if there was very low correlation in the FSCs, right, at low resolution. That would be something to be worried about. And then if you see very odd features, we expect to see a sort of, you know what an FSC curve should look like. That might be an indication, but I don't know what I would do if I saw that. I would just worry that there was something strange. It's not clear that I would know what to do to fix it if it indicates something specific, but maybe others have other experiences.
What are these odd, I mean, if others don't, I assume people can add on, but what are these odd features you're talking about that we must be looking out for when you're looking at a map model FSC?
Well, I'm just saying that generally an FSC curve, you know, typically has quite high correlation values at low resolution, right? In the low resolution part of that plot.
Yeah.
And as you go to higher and higher resolution, higher frequency information, that falls off, right? And goes to a low value. And you have a sort of a, yeah, I think everybody's familiar with what those curves kind of look like, right? Both for a map to map and a map to model. They're similar, they're not the same, but similar. And what I'm saying is that if I were given an FSC curve that had very low correlation values at low resolution, that would be worrying, right? That would, why is that? We don't expect that. And if there are a lot of very, say, sharp changes in the Fourier shell curve as you go out to higher resolution, higher frequency, that would make me wonder about what's going on as well. So those would be things that would be of concern, but as I said, it would just make me think that there is something not right, but I wouldn't know what to do about it. There's not I don't know of any standard approaches to that.
All right.
Right, just to add to it, I mean, map model FSC has very distinct shape across most maps and models I've ever seen. So if you look at 10 or 100 FSC curves, you'll train your eye to know what the good one looks like and what the bad one looks like. So I guess just look at many and then you'll know.
Yeah, if I may ask another one, which is, suppose you have built some high resolution features. I've been asking this question a couple of times in the chat, but let me just ask it right away. If you have built some high resolution features in a low resolution map, will they be flagged up in the map model FSC, or is just a cross correlation values of, let's say, CC ligands and so on?
Well, well, if we think about a ligand, for example, placing a ligand in a structure is not going to change the FSC particularly, right? Because it's a very small part of a big structure. So I wouldn't expect that to change much at all about anything, if that's the question.
My question would be, can you really see the ligand in low resolution maps? I remember you were mentioning like 7 action resolution maps. Can you really see ligands in those maps?
No,
Yeah,
it has been derived from the high resolution map, exact same.
Yeah, that's where I'm going. So if you don't see them, don't place them. And if you do place them, then that doesn't look right to me.
Right. Yeah. So you should be careful. Clearly, you can, if somebody has created a nice high resolution model against high resolution data, and that's somehow related to your map that you've made, you can place that model in your map. Yes, for sure. But that is one of the reasons you have to do things like set the atomic displacement parameters, right? You can't take somebody's model that has very it contains information that says the atoms have this amount of motion and put that in your low resolution map, because that's not realistic. That's one of the reasons you want to try and come up with reasonable displacement parameters. When it comes to things like ligands and waters and things like that, you're not going to see those in the 7-angstrom map. And even though you might believe that they're based on the biochemistry and maybe this other structure, it's a little bit unreasonable to put those into your low resolution map, because you've got no evidence they're there. You've got evidence the protein is there, I imagine, because you can see the envelope for the protein. But anything else, those details, you can't really claim are there.
You were also saying that there might be no discernible change in the map model FSC, even if you put them. Oh, well, that doesn't say anything, but I was just worried that it might throw up in the map model FSC.
No, if you add a little ligand, or even a large ligand, to a whole huge protein structure, the contribution of that ligand to that FSC will be negligible. So you won't see anything in the FSC. So, but if you don't see any density for it, you shouldn't put it in anyway, right? That's not reasonable.
So just to add a little bit to this, some experiments I've done previously, it's even at say 4 angstroms, it's amazing how much you can rearrange a model and not change the map to model FSC substantially at all.
Right.
Right. There is just so much freedom to move in a map of that resolution. It's life, really. So just to add a little bit to Yakomba's situation here, this is a slightly special case in that these 7-angstrom particles are actually from the same set of cryo-EM images as much higher resolution reconstructions of a larger complex containing the same proteins. This is just a smaller fragment of the larger complex that is able to be reconstructed separately. And so probably does actually have the same ligands in it, but as you say, you can't actually see.
Yeah, no, and I can see there'd be special cases like that. But I think I'd want to be in a paper publication. I'd want to be very, or a deposition.
Absolutely.
Very clear about what this all means, right? Because you have to. Everybody on the line here should realize that a lot of the people that go and use the structures that we make they don't understand how the structures are made. They don't understand the details of the experiment, and they just take them as if they're gospel, perfect and accurate. And we've seen plenty of times today that that's not true. And so a biologist that comes along and gets your model and sees a ligand in there when you didn't actually have any data for it, will assume it's all true. So you want to be very clear with somebody, what was your evidence for that ligand? And if your evidence was it was in another structure that was prepared under the same conditions, you just got lower resolution, that's an argument, okay, but you should explain that to somebody in the paper and the deposition.
Can I stretch this slightly to other side? So what's the logic for putting amino acids at a 7 angstrom map, you wouldn't just cut off the side chains and then even though you do not see it in the so-called the feature of the map, it's 7 angstrom.
Right.
Yeah.
So
what are the reasons here?
That's a good question. So there's a bit of a difference though, right? Because you expressed a protein or you got a protein from somewhere, and you saw, you see the volume for the protein in the map. You can be fairly confident that the side chains are on that protein, right? They didn't all fall off. Yeah, that's pretty unlikely to happen. So the fact that you see a protein and it was expressed, and if you have good knowledge about that protein, then it's reasonable to assume that the side chains are there. They might not be visible in the map because of the resolution, of course. Something like a ligand or a water, sure, the ligand might be there, but you've got a lot less confidence because what if something happened during the experiment such the ligand didn't bind, for example? So things that aren't sort of covalently attached, you've got a lot less confidence about their presence. So that's the sort of difference between the two. People do sometimes submit and deposit models which they have made polyalanine or poly-UNK. Nigel mentioned that particular residue. But that's normally because they don't know what the sequence is, or they can't register it properly, so they don't have a reference model at a high resolution. So those models do exist, but if you actually have basically the same structure, protein structure from somewhere, as I said, you can be fairly confident the side chains are there. They haven't disappeared.
So finally, I have one more question, which is about the secondary structure annotation, which is not always perfect, as Pavel mentioned. So how would you go on about that after real space refinement? Do you go to a part which you think should be an alpha helix and then you go and manually annotate those regions as an alpha helix after real space refinement before deposition? Just as an example, I assume there might be many other cases.
Well, I'll let others speak as well, but I would say, yes, you need to use your best knowledge to annotate for restraints. If you're going to use secondary structure restraints in a low resolution, you have to. You're going to have to.
Not restraints, sorry. This is just annotation.
Yes. Well, so there's
secondary structure annotation.
You want to use those secondary structure restraints in refinement to maintain the structure, and then check. So when the deposition is created, it will create the annotation, and that's based on the structure, right? So if you got your restraints right, hopefully the annotation will be correct, but you still need to check and modify it accordingly if it's not.
All right. Thank you.
There is one complication there. In our favorite horrible structure, they actually annotated the helices quite correctly. But if you run DSSP or Ramachandran on them, that will not be correct. And so if you did it right, it should all go together the way you were saying. But if you think it was really an alpha helix, but you fit it with a peptide around backwards, you should fix that peptide, and then your annotation will come out right.
Yes, no, that's a good point, Jane. You shouldn't deposit a model where the structure is all wrong and then just give the annotation you think should be correct. It should match the model, and the model, you should correct the model to make it right. Yes, that's a very good point. So I know that Anna has a hand up, so I wanted to let Anna ask a question. Sorry, Anne. Sorry, you got that wrong, Anne. You're on mute. Sorry, Anne.
Thank you. I don't know if this question fits. Anyway, for a project, we are currently interested in simulating maps using electron scattering factors from a PDB to compare that to a cryo-EM map. So we're using Phenix F model for that currently. However, as Pavel mentioned, that Phenix real space we find does not use structure factors at all, and F model produces an empty Z file. I'm currently wondering if we can actually really compare a map that we get from Phenix F model with a cryo-EM map, or if that's actually not possible.
So I'll let Pavel speak to that.
Yeah, so I wouldn't mix and confuse two issues, refinement and actually calculating structure factors from atomic model. So for refinement to work and drive your model into the map, it doesn't really need to know form factors and calculate or simulate model maps, speaking of cryo-EM jargon. So when it comes to creating or simulating map from atomic model to compare with actual cryo-EM map, yes, we have a tool, number of tools, and Phenix.F model is one of them. So you need to use appropriate scattering factors, which are electron scattering factors.
Yeah.
So which is a good approximation at the moment, but there are shortcomings, which include that we don't really take into account charged atoms and ions. So those are going to be artificially different simulated map versus your experimental map. And really, you're asking about something really cutting edge that we are working right now, and mostly Dorothy is working on. So that's we together work on this project right now with people from UCLA, and so as a first approximation for you to keep going, yes, you can use F model. You calculate your map from F model. Don't forget to set up some table to electron. And that's okay, an approximation, but can be better, can be more accurate, and this is something we are working on to make it actually better.
Yes,
so
I think,
once again, you shouldn't confuse it with refinement. So refinement is one thing; it doesn't need to know exactly form factors and such. But when it comes to calculating map, you need to specify correct form factors, and Phenix.F model is the tool to do this.
I have two more questions concerning that. I mean, since you mentioned the shortcomings, so since we are interested in charges and we are able to already edit our own custom, not very perfect parameters for charged atoms into the scattering pie, what I honestly realized is scaling to the velocity is not implemented anywhere currently in the scattering tables.
No, so that because that's not, so to understand a little bit, I think the history of those scattering factors. So the electron scattering factors are actually, as I understand it anyway, are based on a mathematical conversion of X-ray scattering factors, actually. And in the X-ray case, there is no dependence on the wavelength or the velocity, what we're going to call it. So that's not intrinsically something part of the table. No, so that's not part of the way the math is done. Mm. So yeah, that is one issue. There is this, we're working on something that is not reliant on that, as far as we understand, and that maybe will be sufficient. But we need to see. But yeah, right now you wouldn't, even if you could supply the parameters. There are these formulations which you're aware of. I know I'm completely sure of the formulations that do rely on the wavelength. If you could supply those to Phenix, we couldn't use them in the way that you would want right now.
Mm-hmm. And last question is concerning the atom displacement factors. Now, I do have the special case that the PDB that I'm using to simulate the map was actually refined against the cryo-EM map I'm going to use to compare it to later. In this special instance, actually, the atom displacement factors in the PDB should match what I'm actually expecting in the cryo-EM map.
Mm-hmm.
So I think I wouldn't need to change them, but if I would have, say, a PDB from another structure, would I then change the atom displacement factors values to a certain value, or?
They need to be refined really against the map.
Okay.
You can't a priori just assign values. No, they need to, currently certainly they need to be optimized in an iterative way.
Okay, if I use a different PDB, just do a real space refine and then run the whole thing. Okay, thank you very much.
Great.
I have one question.
Yeah, Prince.
Yeah. Hi, my question is to Pavel. So I think I asked during the chat also that it's something about weight matrix. And so first question is the weight matrix in the code we see and the weight option in the refinement, both are the same thing, or it's totally unrelated?
Unrelated.
Okay. So, okay, I happen to, I was working with 4 to medium resolution map, 4 to 5 angstrom map. There, the clash score was really in the range of 30, 40. And then I was trying to reduce it by doing, by trying many options. So one of the thing I tried playing with the weight while doing the refinement. So I tried a range of, so first I tried with the default parameters, but it's again in the same range. Then I tried with playing with the weight, and then I tried 1 to 5. So at something like 1.5, I found clash score is really getting better, maybe close to 10, and the correlation coefficient is unaffected. And all this Ramachandran outliers and everything is getting better. So my question is whether it is a right way to do that. Can we put the weight option manually if we are getting a better statistics and the map fit is unaffected? So can we do that?
So that, just to be clear, this is the overall, this is the weight between the map and the model, right?
Yes.
So
there's an option in the refinement parameter that we leave blank, and then we talked also that we should keep it we should leave it blank so that it will do the automatic option. So can we enter that thing manually if we're getting a better statistics and slightly better fit between map and model?
Yeah, you can, and the thing again goes back to the simplistic data target function that we use. So at low resolution, imagine you have a helix, which is a tube, and the lower resolution you get, the narrower that tube is. So ultimately, at very low resolution, if you refine a helix against that tube, then atoms are going to be squished towards the center, towards the axis of the helix.
Mm-hmm.
So just inherently refining against low resolution, using the target we use in Phenix field space define is going to, by definition, try to crank up your clash score. So in this case, if you start out with a nice model, it's totally valid to increase weight up to the point where you see the meaningful geometry. So that's just dictated by the target function we use. So I think the answer to your question would be yes, you can, if the default value of the weight doesn't work as well as we hope in your particular case, you can try put more emphasis on restraints to help create better geometry, more meaningful geometry.
Okay, so actually, since I'm a beginner, I have been working for only 6 months. So earlier I couldn't understand, I thought the two weights are the same. And then I estimated the weight in, so there is an estimation, there is a default value of 60, we see in COOT. So I did an estimation, there's an estimation option, and then it says some other number. So then I knew that, like, I don't know if it's sufficient about this, but I tried that number while doing the refinement, by running the refinement by chance. And then I started playing with those numbers, like plus or minus values. So there I started getting a better number without affecting the fit. So in that way, I thought, can we do that manually?
So as Pavel said, it's always, you have the box that allows you to do that. So of course you can do it. In general, we try to make sure that the automatic option is reasonable, right? But yes, if you have some special insight and you find something a bit better, then of course you can do that. That's fine. But you do need to be careful. You do the right thing by looking at the fit and other metrics, right? Because you have to be careful that you don't just turn off the data and then everything else looks great, of course. So you have to look at everything together to know whether it's an answer. And you should also, I think people should realize that overall correlation is a fairly, you know, it's just one number. And so changes in the fit of the model to the map, it's not going to say much about the details. So it's just people should be aware of trying to optimize that model to map fit as a criteria. You probably need to be careful about that, especially because there can be things like the scale of the map and the magnification of the map, other things that might be problematic.
So I have impression that if the fit is not being affected, so and the statistics are getting better, so yeah, we can try, as long as it is happening, we can try that, right?
Sure, but I would also say that, and I'm sure Jane would say this, we should also go and check if there are clashes that show up as problems. Go and look at them. Okay. We always go and look at the model. There is no alternative to looking at the model. We can't automate all of this for you. I think Tristan wanted to say something as well.
That's exactly what I wanted to say. So.
Okay.
I see. Got it. Yeah. Thank you.
Yeah. So you know, we write, all of us write these great programs, and we hope they're very useful, but they're not magic, and there is no alternative for you becoming collectively becoming more expert and actually looking and understanding and trying to address the problems directly. If we get to that point where you don't have to do that, we'll let you know, but we're not there yet. I know David had a question as well. Sorry, David.
Yeah, so I was wondering what the current opinion is about whether you should add hydrogens to your model before you refine. I've tried with and without and tend to get better validation scores when I use hydrogens. I just wondered whether that's a valid thing to do.
Can I answer that one?
Sure, go ahead, Jane.
My answer is yes, you should put them in because they're the only thing that lets you use clashes and hydrogen bonds accurately in the refinement.
Yes.
And you know, again, the hydrogens don't fall off any more than the side chains do in the actual protein or nucleic acid. And the reason for having them is that the restraints from their interaction make the refinement better. It's not just that the validation is better, but you're actually getting a better fit between things.
Yeah, I'm certainly seeing that, yes.
I did that for very many years in even high resolution structures, and we're convinced that you actually should.
Yeah, and we actually would advocate pretty much the same for crystallographic refinement as well. And maybe not in the very early stages when the model maybe has serious errors and you maybe don't want to get the wrong things interacting with each other, but certainly later on in refinement.
They do actually hurt going over barriers in the refinement.
Yeah, but once you feel the model is in pretty good shape, you know, reasonably, then definitely it's a good thing to include in both kinds of domains. Yeah.
Okay, thank you.
I'd like to thank everybody who spoke today. So Pavel and Nigel and Jane, thanks a lot, everybody. Thank you. Thanks for all your effort giving those talks. And thanks for everybody who's been online. Great set of questions. Thank you, everybody. We'll finish today and stay safe.